Welcome students. Today I am going to discuss about the theory behind vibrational spectroscopy, or it is also known as infrared spectroscopy. Like any other spectroscopy, it is also the resultant of light and matter interaction. In this case, a matter or a molecule interacts with the light of having frequency range in the IR region, mainly in mid-IR region, from 400 to 4000 centimeter inverse. So, when a molecule interacts with the light having frequency range from 400 to 4000 centimeter inverse, a transition happens between its vibrational energy levels. Okay, and due to this we get the corresponding spectrum of the molecule, and the spectrum we generally get as the transmittance of the light as a function of wave number or energy in centimeter inverse, wave number basically. And when a molecule interacts with light, depending on the nature of the molecules, depending which type of atoms present in the molecules, which type the bonding connectivity, whether double bond or single bond, nature of the bonding, depending on the nature of the atoms, nature of the bonding, and also nature of the functional groups, each and every molecule has their own vibrational spectroscopy or distinctive vibrational spectroscopy, which is different from the other molecules. So vibrational spectroscopy is very much important. We can get many informations by analyzing the IR spectroscopy or vibrational spectroscopy of a molecule, and we can either identify the molecule to a greater extent. So, and in every exams, from +2 level to in MSc level, in any competitive examination like joint entrance and a NET, CSIR, NET, GATE, many exam we get question from the theory of vibrational spectroscopy. So this is a very important topic, so keep watching this video very carefully. I'll be discussing whole theory, and also I'll be solving some problems, so keep watching this video. Let's begin the theory behind the vibrational spectroscopy. Whenever you open any book to read the vibrational spectroscopy, you see this kind of potential energy curve versus the internuclear separation. Okay, so y-axis present the potential energy of the molecule, and x-axis the internuclear separation between the atoms, which forms that particular molecule. So here, suppose a simple heteronuclear diatomic molecule HCl. Okay, now if the molecule is in the ground state, now what is vibrational spectroscopy? So when a molecule interact with the light having frequency range from 400 to 4000 centimeter inverse, it the transitions happens between its vibrational energy levels. Okay, like rotational energy levels or electronic energy levels, molecule also has some vibrational energy levels. So when this particular range or this particular frequency of light interacts with the molecule, the transition of the molecules takes place between its vibrational energy levels, and thus we get this kind of spectrum of the molecules. And during this vibration, some changes happen within the molecule, and basically this potential curve depend on the change in the bond distance between the atoms. Okay, and also like any other spectroscopy, vibrational spectroscopy also the resultant of the light matter interaction. Okay, so when a molecule like heteronuclear molecule like diatomic simple molecule like HCl, it interacts with the light having frequency range from 400 to 4000 centimeter inverse, the equilibrium distance, suppose HCl molecule when it is at ground state, okay, it does not interact with the light at that state, the bond distance between H and Cl is R equilibrium. So when it start interacting with the light, the bond distance will no longer be R equilibrium. It could either be elongated or be compressed. Okay, and due to this reason, it will, the molecule will goes from lower energy level to higher energy level, and during this process bond distance between H and Cl atoms will also be keep on changing. Okay, so suppose here elongated bond, here compressed, so Cl atom, suppose we fix the position of H atom and only the position of Cl atom keep on changing during the transition between the vibration energy levels. So here if chlorine atom goes from this to this position, so after vibration if we want our molecule back, okay, so the chlorine atom should get back its position to to maintain the equilibrium distance between H and Cl. So a restoring force must work there against the displacement, okay, to get back the chlorine atom to its initial position. So our system must work as simple harmonic oscillator, or our system should be inelastic in nature. So this system should follow the Hooke's law. So during vibrational transition, it has been assumed that the system behaves like a simple harmonic oscillator, and it follows the Hooke's law, where Hooke's law means the restoring force, okay, which works against the displacement, okay, that is proportional to the displacement, and F restoring is equals to minus K into X, where K is the force constant. It is a proportionality constant and known as force constant. And as much as K is higher, the bond between two atoms or any atoms, is more stronger, and you need more energy to stretch or to compress that particular bond. And so if suppose for HCl, this is the curve, potential curve, for HF we will get more steeper curve. The wall, this wall and this wall will be more steeper in nature, because it is more difficult to stretch or to compress the HF bond compared to HCl bond, as the force constant between HF is much higher than HCl. Now let's talk about the Hooke's law. So it behaves like a simple harmonic oscillator and follows Hooke's law. So F is equals to minus K into X. X is the displacement. Okay, displacement here from R equilibrium to R. So the displacement is only this. Okay, so it will be R minus R equilibrium. Now So when you stretch, or when you know when the bond gets elongated, see the position of Cl atom, you know changes from this to this. So work done on the system, some work done on the system, so that work done will be force into displacement. Okay, so we can get this work done by integrating the force over infinitesimally small distance. So we can write the work done on the system is equals to minus of integration f into dr. So here f we can write k into r minus re, minus k into r minus re. So here we put here minus k into r minus re. So it is minus half. By integrating this we get minus half k into r minus re square. So minus half into k x square. So it is a parabolic potential. So work done here for simple elastic stretching, or for elastic force, we know that if something work done, that is stored as potential energy in the molecule. So work done here we can consider it as potential energy stored in the molecule. So that is in minus half kx square. So that is parabolic potential, because y is equals to ax square is the equation for parabola. So this is the another interpretation why we get this kind of parabolic potential curve with respect to the internuclear separation. To the next important thing, which is the energy of the each vibrational energy levels. So if we consider this whole curve as the wheel of energy, so if potential energy is stored here, so this potential whole wheel is composed of some potential energy levels, having different quantum mechanics. We know that any molecule can have some discrete amount of energy. Okay, so it cannot have any energy, so it only can have some discrete amount of energy. And also here the whole potential wheel can be divided into some discrete energy level. And it is assumed that for simple harmonic oscillator, these levels are equally spaced, means that energy difference between each two levels are same. And the expression of the energy for each level is V plus half h nu in joule. V plus half h nu in joule. V is the vibrational quantum number which is from 0, 1, 2, 3, any integer. And why it is in joule? Because we know that h is Planck constant in joule second, and nu is the frequency in second inverse, so h nu will be in joule. Or another form we see in centimeter inverse. Basically in graph of any IR spectroscopic graph, we see it in centimeter inverse. Okay, and it is written as wave number. So how we get wave number? If we divide energy by hc, so we get E V prime V plus half h nu by hc. So h cuts here, so only h nu by c. So nu by c we can write it nu e bar or omega e bar, and it we get E V prime we get in centimeter inverse. Okay, so how centimeter inverse? Here we see that h we cut here, so nu in second inverse, and c is the speed of light, semi second inverse, so it is in centimeter inverse now. And in somewhere you see or it in nu e bar, or somewhere we can see it in omega e bar. So both of them are same. Okay, so this is the expression of energy of each energy level, in joule or in centimeter inverse. And how we get this expression? By solving the Schrodinger wave equation, and by assuming that each energy level are quantized, and a molecule or a particle can only have some discrete energy. Okay, discrete value of energy, not any value. Okay, next, 0 point energy. This formula is very much important. When you put value v as 0, v here we put 0, we get half omega e bar in centimeter inverse, or half h nu in joule. So this is the 0 point energy. You should remember this formula. And you see here that 0 point energy of any molecule is not 0, means whether the molecule at the ground state, you are not providing any external energy, then also it possesses some energy, potential energy, by virtue of its position. So of a molecule or a particle is not 0 whether it is in the ground state. Now the expression for nu or nu e bar or omega e bar. So nu is 1 by 2 pi. This is for the frequency for fundamental transition. Means the fundamental transition means you are assuming the transition from v is equals to 0 level to 1 level, because we know that ground state level is always mostly populated. So whenever the transition will take place, the most intense transition will take place from 0 level to first excited level, and this frequency is the expression of the frequency of the fundamental transition, and this is 1 by 2 pi root k by mu for the mu, and or omega e bar and nu e bar is 1 by 2 pi c root k by mu centimeter inverse. So k is the force constant we already discussed, and mu is the reduced mass of that particular molecule. So if reduced mass is higher, nu e bar or omega e bar is lower, means you need less energy to stretch or compress that bond, or to make any changes in the bond. Or k is higher, means force constant is higher, means bond is more stronger, so you need more energy. So using this equation, we can if k and mu is given, we can determine omega e bar or frequency for the transition. And if omega e bar is given, means frequency is given, fundamental vibration frequency is given, and mu is given, means that the mu is given, then you calculate the k, force constant also. So using this equation, we can determine many things. Okay, the difference between two energy levels. Suppose for fundamental transition, the energy difference from v is equals to 1 to v is equals to 0. So we know the expression for energy v plus half omega e bar. So minus of v plus half omega e bar of 0 energy level, this is for the energy level v equals to 1. So for 0 point energy, we know that half omega e bar the value, and here if we put v is equals to 1, we get 3 by 2 omega e bar. So this is the omega e bar only, and this is also the same for the energy difference between v is equals to 2 to v is equals to 1. Okay, so here if v is equals to 2 to 1, we want to know the energy difference. So here we have to subtract the energy of V is equals to 2 to energy of V is equals to 1. So if we put here 2, we get 5 by 2 omega E bar, and we know that the energy of V is equals to 1 level is 3 by 2 omega E bar. So we put here, we get omega E bar centimeter inverse. So for simple harmonic oscillator, each energy levels, each quantized energy level is equally spaced. Okay, each level is equally spaced. So from that we can assume that we can get only one peak for a simple heteronuclear diatomic molecule like HCl, because if the suppose the for V is equals to, for the transition from V is equals to 0 to V is equals to 1, it absorbs energy at that particular position. Okay, at that particular position it absorbs energy, and this is then again for further transition from V is equals to 1 to V is equals to 2, it needs same amount of energy. So if it absorbs energy omega E bar, okay, it need energy omega E bar, okay, for the transition of V is equals to 1 to 0 to 1, that it needs the same amount of energy for the transition from V is equals to 1 to 2. So if we get a peak for the transition 0 to 1 at that particular position, this the next peak for the transition 1 to 2 will lie above this particular peak. So we will get only one peak for all possible transition for a simple heteronuclear diatomic molecule like HCl. Okay, so for a simple harmonic oscillator we will get only one peak, but basically for true molecule, when energy level increases, means molecule vibrate at higher energy level, it does not follow it does not behaves like a simple harmonic oscillator, and instead of one peak we get several peaks having different intensity, and at they appear also at different energy, different frequency region, because as they behave like an harmonic oscillator. Okay, now let's see one problem where force constant has to be determined, where the fundamental vibration frequency is given for SHO. It is at 2140 centimeter inverse, and also the atomic mass of C and oxygen is given, carbon and oxygen C12 and oxygen 16 is given. So from this we can calculate the reduced mass, that is the product of two mass by the summation of two mass, and this has come out as 1.14 into 10 to the power minus 26 kg. Now we want to calculate the force constant, so we have to put this we have to take the equation nu E bar is equals to 1 by 2 pi c root k by mu, that I already discussed that this equation is very useful equation, and we can determine many things from this equation. Okay, so here we also know the nu E bar value, that is this, so you put here this, and we can calculate k as 4. If we want to calculate k, we have to square of this, both side we have to square the both sides, so we get k is equals to 4 pi square c square nu E bar square mu. So if we put all the value, we get it, the force constant, as 1853 Newton per meter. So if instead of nu E bar, the force constant and the mass of atomic mass of carbon and oxygen were given, then we can calculate, then by using force constant value and mu, we could calculate nu e bar, the fundamental frequency also. So this equation is very useful. Now the selection rule. So as a whole, the gross selection rule for allowed transition for vibrational spectroscopy, like the rotational spectroscopy of a rigid rotator, there we see that delta J plus minus 1, delta J is equals to, here also the difference between two quantum levels should be plus 1 or minus 1 vibrational quantum levels. So if we consider a transition from v is equals to 0 to v is equals to 1 is possible, or 1 to 2 is possible, but from 0 to 2 or 0 to 3 is not possible. But in reality, that also, those transitions are also possible, and it violates the rule of simple harmonic oscillator, and a molecule behaves like an harmonic oscillator, which I will be discussing later in the next part of my vibrational spectroscopy video. But for simple harmonic motion, the gross selection rule is delta V plus minus 1. And also the main condition to be a molecule IR active, there should be change in the dipole moment during the vibration. Dipole moment, we know, charge into distance. So if you consider HCl molecule, charge we cannot change, only distance we can change. So if distance is elongated, then there will be increase in the dipole moment with respect to distance, and it's compressed, there will be decrease in the dipole moment with respect to distance. So this value d mu by dr must not be 0, it should have some value. So the main condition of a molecule to be IR active, that there should be a change in the dipole moment during the vibration, so that we can get the IR spectrum of that molecule. Thank you for watching this video. So in this part, I have discussed only about the simple harmonic motion. In next video, I will be discussing about the anharmonic part of the vibrational spectroscopy.